So this is the quick and dirty on what we're learning in class right now, which is on 3.5. So we're talking about Cauchy's bound and rational roots theorem. And so I remember when we were using graphing calculators and finding the solutions, and I told you it's going to get harder because we're going to be doing this by hand. This is the we're doing it by hand thing. So because you guys are gone and I want to make sure you're not falling behind, we're just going to kind of do the best that we can. So if Cauchy's bound says that if m is the largest coefficient in a polynomial and a sub n is the leading coefficient, then all roots can be found on the interval negative m divided by a sub n minus 1 and m divided by a sub n plus 1. So all this is saying is that all of the possible intercepts for a polynomial are going to be between these two numbers. So let's put this into action. And we're going to find the bound of the function f of x equals x to the fourth plus 2x cubed minus 12x squared minus 40x minus 32. So looking at that, I need to find my m and my a sub n. And the reason why is because I can't even use this formula if I don't know what m is or a sub n is. So m, remember, is the biggest coefficient. So looking here, actually, I want this tool. The biggest number in this whole polynomial is 40. So that is actually going to be my m value. And I don't care that it's negative 40 because we're looking at the absolute value of m, and the absolute value of negative 40 is 40. So I'm going to say m equals 40. Okay? The next thing I need to find is a sub n. And a sub n is the coefficient of the leading coefficient, was coefficient of the first variable. So the leading coefficient is 1 because it's attached to x to the fourth. So that's going to be my leading coefficient. I'm just putting it there to kind of remind you that there is actually a number there. So let's write that. Oh, that in green. There we go. So, and blah, blah, a sub n. And that is equal to 1. Then Cauchy's bound says that my intercepts are going to lie between 40 divided by 1 minus 1 and 40 plus 1 minus 1. And actually, it's negative 40 minus 1 and negative 40 over 1 plus 1. So let's go ahead and put that into action. So the bound is going to be between negative, and then I'm going to have 40 over 1 minus 1 and 40 over 1 plus 1. And if I reduce that, then I'm really just looking at negative 40 minus 1, which is negative 41, and then 40 plus 1, which is 41. So what this means is that my intercepts are all going to lie between negative 41 and 41. So if I get a number outside of that bound, it's not actually a solution. It's not worth me testing. Okay. So the next part is that now we have found the bound, we need to use a rational roots theorem. And what that says is that all possible rational roots, and the roots are the intercepts, so in rational means just like whole number or fractions, can be found by dividing the factors of the last term by the factors of the first term in a polynomial. And so the formula we're going to use is RR for rational roots equals plus or minus P divided by Q, where P is the factors of the last term and Q is the factors of the first term. So the reason why we want the rational roots is because this is going to give me a list of numbers of all the possible things that could work or that could possibly be horizontal intercepts given the equation. So again, still looking at that same equation, I'm going to now identify the rational roots. So to do that, I need to identify my first term and my last term. So the first term of this function is 1, and that is my Q value. So Q, so write first term gonna be one more good. Actually, you know what? There we go. So first term is equal to q. Remember we said the first term was q. And so first term is q, which is 1. And then my last term is the very last number in here. Remember that's equal to p. And my last term is 32. Again, it doesn't really matter that it's negative. So now that I have my p, I have my q, I'm going to list all of the factors that are possible. So the factors are numbers that multiply into our term. So factors of 1, which is q, remember, just put that in parentheses, are just 1, right? 1 is the only thing that multiplies into 1. P is a little bit different. So factors of p, which is 32, that I'm going to have a lot of numbers because a lot of numbers go into 32. Like 32 goes into 32. 16 goes into 32. 8 goes into 32. 4, 2, and 1. Now keep in mind that these are all the positive roots. I also have negative roots. So all of these factors can be positive or negative because negative 1 times 1 is 1. Likewise, negative 32 times negative 1 is also 32. So for each of these numbers, it is going to be plus or minus. And that's really important to just keep in mind. I'm just putting it on the outside because I don't want to write for everything. So now that I have the possible factors of p, I have the possible factors of q, I actually need to identify this set of all the rational roots. So rational roots RR is going to be equal to, let's start putting all these guys together. So it's plus or minus p over q. So plus or minus, and I'm going to copy this because I'm going to use it a lot. First one is 32 over 1. After that, I'm going to have plus or minus 16. Oops, that was 61. 16 over 1. I'm still a little bit again. And then I'm going to have plus or minus 8 over 1. And then plus or minus 4 over 1. Plus or minus 2 over 1. And plus or minus 1 over 1. So those are all of my possible rational roots. And obviously all of these fractions can be simplified. Side note, if my leading coefficient was 2, then my factors would have been 1 and 2, right? So in that case, I would have all of these numbers over, sorry, I just realized that there's this weird bracket hanging out here, over 1, but then I would also have to put them all over 2. So keep that in mind because when you get bigger numbers, you do have to put it over all the factors. All right, so let's simplify this. So if I simplify this guy, I'm really just looking at the factors of plus or minus 32, plus or minus 16, plus or minus, oh, that's why it's doing that. Eight, because again, all I'm doing is dividing by 1, which is giving me the same thing. And you want it simplified because at some point we're going to use synthetic division, and in that case, you're not really going to be dealing with a fraction. I mean, you can, which is not very fun. So these are all the possible rational roots. So I could still have something irrational like square root of 2, but my rational roots are going to be 32, 16, 8, 4, 2, or 1. Those are all my possible roots. It doesn't mean it's going to be all of them, but it gives me a nice smaller sets. Remember here it was saying it's between negative 41 and 41, and now it's like, okay, so yeah, it's between negative 41 and 41, but these guys right here are what it's actually could possibly be. So we went from a range of a lot of numbers to just a couple. So that's really nice. So let's put it all together. To find all of the rational roots, you're going to have to follow these steps. So first one would be to find the bound. Then we need to find the rational zeros. And then we're going to graph it. After that, we'll identify all of the possible solutions. Choose a solution to plug into synthetic division and test. It must be a rational root, so we're not going to test like square root of 4. And then we're going to repeat it until we reach a quadratic. And the reason why I want a quadratic is because once we get a quadratic, we know how to manipulate that. We can factor it, we can use BixX, and we can also use the quadratic formula and group factoring. And then we're going to write our answer where x is equal to blah, 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 whatever number it is. So we're going to find all of the rational roots of that same function we've been working this whole time. So we have step 1 and 2 because we just did it up here. So all I did was copy and paste that down here. So I have my bound, I have my rational roots, and now I'm going to use a graphing calculator to identify the possible rational roots. Okay, so what I did was I graphed this function x to the 4th plus 2x cubed minus 12x squared minus 40x minus 32. And it got me this graph. And so if I look, it looks like one of the intercepts is at -2 and one of the intercepts is at 4. And like it's pretty obvious it's there, but I need to test using synthetic division. So I'm just going to go with 4 because I like even numbers. So what I'm going to do is I'm going to go back to the other one, and I'm going to start using synthetic division on this equation right here with 4, x equal to 4. All right, let's just turn on. Okay, so using x equal to 4, let's start doing synthetic division. So remember when I set synthetic division up, I'm going to make my t. Let's go, Tigers, let's go. So I have this and that, and I'm going to just go put my numbers. So I got 4 here. And then over here, I'm going to just put my leading coefficients. So I got 1, 2, -12, -40. Okay, I don't care. And then -32. Oh, I keep doing that. All right, ignore the fact that it keeps doing that. So dropping down the first one, I'm going to get 1. Well, 4 times 1 is 4. And if I add 4 and 2, I'm going to get 6. 4 times 6 is 24. -12 plus 24 is 12. Falling down. 4 times 12 is 48. -40 plus 48 is 8. And then 4 times 8 is 32. Add those together, I get 0, which means that 4 is actually a factor, which is great. That's what I want. So if you don't get 0 in this box, it means it's not a factor, and you got to test a different point. Okay? So since it is a factor, if I can just go ahead, and I know so far one of my answers is that x is equal to 4. Oh, let's see if we can find the other answers. So remember, if we think about that graphing calculator, it also looked like it crossed at -2. So that's the next point I'm going to do. Because remember, after synthetic division, I don't have a quadratic yet. I actually have x cubed plus 6x squared plus 12x plus 8. This is not a quadratic. This is a cubic function. So I got to use synthetic division one more time to get it to be a quadratic. And this time I'm going to test -2. Because when I looked at my graph last time, it looked like -2 was also a possible root. So let's go ahead and drop that guy down. Make our box. Trying to, yeah, it's not going to be great. There we go. All right, and then let's go ahead and put our coefficients in here. So I'm going to have 1, 6, 12, and 8. Those are all my coefficients, and in this box we're testing -2. So dropping down the 1, negative 2 times 1 is negative 2. 6 minus 2 is 4. Negative 2 times 4 is negative 8. 12 minus 8 is 4. Negative 2 times 8 is negative 8. Subtract that, I get 0. Which means negative 2 again is going to be a root. So far we're doing fantastic. So I can write up here, x equals negative 2. Okay. All right, so then now I do have a quadratic, right? I'm going to have x squared plus 4x plus 4. And this is something I can factor. You can use the quadratic formula. I'm not going to. I'm just going to use the big X method because that's what works best for me. So making an X. I'm asking what number multiplies to 4 and adds to 4. It's a pretty easy one, but we'll do the big X method so you can see it in action. So 4 adds to 4. Well, 2 and 2. 2 times 2 is 4, and 2 plus 2 is 4. So 2 and 2, which means my factors are actually of this are going to be x plus 2, x plus 2. Okay? And if I simplify that, if I set these equal to 0, then x plus 2 equals 0, means that x is going to equal negative 2, because all I do is subtract it. And it's the same thing for the other. So actually, I'm going to have negative 2 3 times. So negative 2, negative 2, negative 2, because I have the negative 2 from right here, and then I have 2 more negative 2's right here. If you remember, if you look at the graphing the image that we got on the graphing calculator, negative 2 has multiplicity 3, because it makes that nice little kind of weird shape, like it's got that cubic shape to it, where it goes down, kind of rides at negative 2, and then goes down again. So it makes sense if it has multiplicity 3 that we would have it 3 times. So now that we got this all done, this is our answer. We found all of the zeros. That's what it asked us to do, and we did it without using the zero function on the graphing calculator.